Hello everyone, welcome to the video lecture of this course Finite Element Method. So this is the sixth lecture of the first module that we will discuss today. So in the last lecture we have discussed the Rayleigh-Ritz method, and after that we have started discussing the initial value and boundary value problem concept, and based on those concepts we have discussed two different problems based on the initial value and boundary value problems. So there we have seen that there are actually 7 different steps for the Rayleigh-Ritz method, and for the beam or bar element we need to follow those 7 different steps to solve those problems based on the concept of the Rayleigh-Ritz method. Now, today we will be continuing that lecture, and today we will first discuss the boundary value problem, some more problem regarding the boundary value problem concept, and after that we will discuss the weighted residual method. So in one of the earlier lecture we have discussed some numericals based on the weighted residual method, like the point collocation, subdomain collocation, least square, and Galerkin's method. Today also we will discuss some more complicated problems based on those weighted residual method concept. Okay, so let us start this lecture. So first problem that we will discuss today, it is the boundary value problem. The concept of this boundary value problem, it was discussed in the earlier lecture. Now let us discuss the numerical based on that concept. So the problem statement is like that: we need to find the solution of the boundary value problem y double dash plus 4y equals to 0 with y pi by 8 equals to 0 and y pi by 6 equals to 1. So that means what? When x equals to pi by 8, then y equals to 0, and when x equals to pi by 6, then y equals to 1. So from these conditions we can easily identify that it is a boundary value problem. Now from the differential equation we need to first write the auxiliary equation, and from the concept of that auxiliary equation we can write the auxiliary equation here, that is lambda square plus 4 equals to 0. So this is the auxiliary equation of the given differential equation. So from this equation we can write that lambda square, this is equals to minus 4. So that means lambda equals to root under minus 4, or this is equals to plus minus 2i. So that means lambda equals to alpha plus minus I beta. Here alpha equals to 0 and beta equals to 2. Now from the concept of the complementary functions, we can write that yx equals to e to the power alpha x c1 cos beta x plus c2 sin beta x. If we put the value of alpha and beta here, then e to the power 0 into x, that means e to the power 0, then c1 cos 2x because beta equals to 2, and c2 sin 2x. That means yx equals to e to the power 0 equals to 1. If we know this, then yx equals to will be c1 cos 2x plus c2 sin 2x. So this is our equation number 3. Now if we apply the boundary condition in this equation number 3, then we are getting this: when x equals to pi by 8, then yx equals to 0. So that means the equation 3, it will be 0 when we will put the value of x equals to pi by 8. Now putting the value of x equals to pi by 8, we can write y pi by 8, this is equals to c1 cos pi by 4 plus c2 sin pi by 4. So that means putting the value of pi by 4 here, we are getting that equation number 4, that is c1 C1 by root 2 plus C2 by root 2, this is equals to 0. So this is our equation number 4, which we are getting the boundary condition 1. Next, if we apply the boundary condition 2, that is when x equals to pi by 6, then y equals to 1. Now putting the value of this boundary condition in equation number 3, we are getting that 1 equals to C1 cos pi by 3 plus C2 sin pi by 3. So that means C1 3 by 2 plus C2 by 2, this is equals to 1. So this is our equation number 5. Now from these two different equations, that is equation number 4 and 5, we can easily calculate the value of C1 and C2. So from these two different equations, we are getting the value of C1, this is equals to 2.732. Now if we put this value of C1 in any of the equation number 4 and 5, then we can easily calculate the value of C2, and the value of C2 we are getting here as minus 2.732. Now if we put the value of C1 and C2 in equation number 3, then we are getting the final result yx equals to 2.732 cos 2x minus sin 2x. So this is the general equation here, putting the two different boundary conditions which are given in this numerical. So what we have done here, we have first written the auxiliary equation corresponding to the given differential equation. From that we have written the complementary functions in the form of alpha and beta, and in that complementary function we have used the two different boundary conditions which are given here. Now using these two different boundary conditions, we have solved the value of C1 and C2 from the complementary function. After that we have used those value of C1 and C2, and finally we have got the general equation here. So this is the procedure to solve such numerical based on the boundary value problem. So next we will discuss the weighted residual method concept. So it was already discussed earlier. Now today we will be discussing some more complex numericals based on this weighted residual method concept. So in this weighted residual method, it is actually a powerful approximate procedure which is applicable to several problems. For structural problems, potential energy functional can be easily found. So Rayleigh-Ritz method is used, which we have seen in the earlier lectures, how to use the Rayleigh-Ritz method. There are actually 7 different steps where we have first identified the auxiliary function based on the beam or bar. After that we have found the total potential energy based on the strain energy and work done. Then we have found the Rayleigh-Ritz parameter, and lastly we have found the maximum deflection and bending moment. So these are the 7 different steps of the Rayleigh-Ritz method, and based on those we have solved some numericals. Now, on the other hand, for non-structural problems, the differential equation of the phenomena can be easily formulated, and for such type of problems the weighted residual methods, these are very much useful. Now there are actually 4 types of weighted residual methods which are very popular among the others. Now those methods are actually point collocation method, then subdomain collocation method, then least squares method, and Galerkin's method. Now based on the concept of these 4 different methods, we will discuss some numericals today. Now among the 4 different weighted residual method, the last one, that is the Galerkin method, it is actually used in the finite element analysis. Now what is the general procedure for this weighted residual method? in all these weighted residual method, we need to find the value of y, which is actually the solution of the differential equation, which will be given in the numerical. Now, if it is not possible to find a solution, in that case we assume an approximate function for y. After that, we substitute the approximate solution in the differential equation, then we can get the residual, and the residual, which is actually expressed as the function of r x1 a1 comma a2 comma a3, this is equals to 0. So this is the expression of the residual that we will use in those weighted residual method numericals. Now in this expression, a1 and a2, these are the unknown parameters which are present in the assumed trial function. This assumed trial function, it can be expressed as follows, that is y equals to function of x, and that function, it should be consists of the a1 a2 a3 dotted up to an, which are the parameters that should be present in the assumed trial function. And this trial function, it should exactly satisfy the boundary conditions which will be given in the numerical. Now this method of the weighted residual method, it actually needs the parameters a1 a2 a3 up to an to be determined by satisfying the following equation. What is that following equation? That is integration d is actually the domain, then wir function of x, which will be based on the a1 a2 a3, that parameters, and dx, this is equals to 0. Now this w, it is the function of x, and it is known as the weighting function. Now let us first discuss the point collocation method. Now in this collocation or the point collocation method, the residuals, these are actually set to 0 at n different collocations xp, and the weighting function wi is denoted as delta x minus xi. So that means wi is equals to delta into x minus xi. Now substituting this value wi in the earlier equation, that means in this equation 1.10, we are getting this equation number 1.11. Now here these xi's, these are referred to as the collocation points, and these are actually selected by the discretion of the analyst. So that means finally here we are getting the residual, which is a function of x consisting of these parameters a1 a2 a3 up to n, and this is equals to 0. So this is the concept of this point collocation method. Next we are having the subdomain collocation. Now in this method, the weighting function wi, these are chosen to be unity over a portion of the domain and 0 elsewhere. So this wi, it can be written as w1, this is equals to 1 for x in d1, and this is equals to 0 for x not in d1. Then w2, this is equals to 1 for x in d2, and this is equals to 0 for x not in d2, and this similar manner we can write up to wn. Next we are having the least squares method. So in this method, the integral of the weighted square of the residual over the domain, it is required to be minimum. So in that case, I equals to integration over the domain d, the residual square dx, this is equals to minimum. So that means where I equals to function of a1 a2 dot dot an, and this requirement is del ai, this is equals to 0, where I equals to 1 2 3 dot dot up to n. And lastly, we are having the Galerkin's method, and in this method the trial function Nix this is itself is considered to be the weighting function. So that means Wy this is equals to Nix. So here integration over the domain D, Nix multiplied by residual dx this is equals to 0, where I equals to 1 2 3 dot dot up to n. So these are the fundamental concept of the four different weighted residual method. Now based on this concept, now we will discuss some numericals. Okay, so the first numerical, it is given here: the governing differential equation for the fully developed laminar flow is given by mu d2u dx2 plus rho g cos theta this is equals to 0. If boundary conditions are du dx at x equals to 0 and ul equals to 0, then we need to find the velocity distribution ux. So this is the problem given here. So using the weighted residual method, we need to find the velocity distribution for this fully developed laminar flow. And so what is the concept of this fully developed laminar flow? It is already studied in fluid mechanics and in the convection part in heat transfer also. So these things will not be discussed here. We will directly go to the procedure to solve the numerical based on the weighted residual method. Now here, as no trial function is given, so we need to assume a trial function which is based on the polynomial function. Now let us assume the trial function ux is equals to a0 plus a1x plus a2x square plus dot dot. We are considering only the first three terms of the polynomial function. Now let us apply the first boundary condition in the trial function. The first boundary condition, it is given at x equals to 0 du dx this is equals to 0. So from the equation number 1, if we want to find du dx, so in that case it will be a1 plus 2 a2x, because a0 it will be 0 with respect to the differentiation dx. Now if we put at x equals to 0 du dx equals to 0, so that means we are getting the value of a1 this is equals to 0. Next we need to put the second boundary condition, which is given at x equals to L ux equals to 0. If we put this boundary condition here, then we are getting 0 equals to a0 plus a1L plus a2L square. Now here if we put a1 equals to 0, which we got from the earlier condition where we have entered the first boundary condition, then we are getting that the value of a0 this is equals to minus a2L square. So that means we have found the value of a0 and a1. Now if we put the value of a0 and a1 in the question number 1, that is the first equation where we have assumed the trial function, in that case we are getting that ux equals to minus a2l square plus 0 plus a2x square. The 0 is for a1. So that means we are getting the value of, or the mathematical representation of ux in terms of a2, and this is equals to a2 multiplied by x square minus l square. So this is our equation number 2. From this equation number 2, we need to find the second order differentiation. So that means first we need to do the first order. So du dx is equals to a2 into 2x, and after that the second order of this will be 2a2. Now the residual which is given here, capital R, equals to mu del 2u del x2 plus rho g cos theta. This is equals to 0. But the value of d2u dx2 we have already found in the earlier slide, that we have seen that d2u dx2 this is 2a2. Now if we need to put this value of d2u dx2 here, so that means mu 2a2 plus rho g cos theta, this is equals to 0. So that means the value of a2 which we are getting here minus rho g cos theta divided by 2 mu. Now if we put this value of a2 in the equation number 2, so this was our equation number 2, a2 into x square minus l square. Now we need to put the value of a2 here. So that means the final equation for the velocity distribution, here we are getting as rho g cos theta by 2 mu into l square minus x square. So this is the final representation of the velocity distribution. So what we have done in this numerical, the residual it was given here, and the two different boundary conditions were given, and based on this given data we had to find the velocity distribution equation. So for that we have first assumed one trial function based on the polynomial function. In the trial function we have entered the two different boundary conditions which are given. Based on the values of the two different boundary conditions, we have identified the two different parameters in the trial function, which are a0 and a1 in terms of the a2. After that we have entered those values and we have rearranged the trial function in terms of a2, which we can see here in equation number 2. Now from this equation number 2 we have done the second order differentiation of u with respect to x. Now that d2u dx2 we have put that value of d2u dx2 in the residual function, which is equals to 0. So from that we have got the value of the a2. Now that value of a2 we have finally entered in equation number 2 here, and finally we have got the velocity distribution equation, which is the required equation in this numerical here. Now let us discuss one more weighted residual method numerical. So the new problem given is the differential equation of a physical phenomena is given by d2y dx2 plus 500 x squared. This is equals to 0. Now the value of x lies within 0 to 1. The trial function y equals to ai or a1 into x minus x to the power 4. So the trial function is given here, so no need to take into assumption anything. It is given y equals to a1 into x minus x to the power 4. Now the two different boundary conditions are given. y0 equals to 0, that means at x equals to 0 y equals to 0, and y1 equals to 0, that means at x equals to 1 y equals to 0. Now we need to calculate the value of the parameter a1 by the following methods. So by using this point collocation, subdomain collocation, least square and Galerkin's method, we need to find the value of the parameter a1 which is there in the trial function. Now, to solve all such problems, we need to first verify whether the trial function it satisfies the boundary conditions or not. Now in this trial function, you can see if x equals to 0, then y equals to 0, it is satisfying this trial function, and when x equals to 1, then also the y equals to 0. So both the boundary conditions which are given in this numerical, it is satisfying the trial function. Now first we need to find the value of this a1 using the point collocation method. Now in this point collocation method, we know that the residual r equals to 0. So first the trial function y is given. So here dy dx equals to a1 to 1 minus 4x cube. Then d2y dx2, this is equals to minus 12 a1 x square. If we substitute this value of d2y dx2 in the residual given here, then we can directly write the residual function as minus 12 a1 x square plus 500 x square. So this is our equation number 2. Now in point collocation method, the residuals are set to 0. So that means this minus 12 a1 x square plus 500 x square, this is equals to 0. So this is our equation number 3. Now in this problem, we need to find the parameter a1. So that means only one collocation point is needed, and that point may be chosen within the range of 0 to 1. Because that range was given here in this equation, in this numerical actually, that x lies within 0 to 1. Now in between the 0 to 1, let us choose the point half. So substituting x equals to half in equation number 3, we are getting the value of a1, this is equals to 41.66. So that means what? The trial function's equation, this is equals to 41.66 into x minus x to the power 4. Now let us discuss the subdomain collocation method. In this subdomain collocation, the formula is integration 0 to 1. It is the range given here in this numerical. Integration 0 to 1 r dx, this is equals to 0. Now here the value of the residual r, it is actually minus 12 a1 x square plus 500 x square into dx, this is equals to 0. So first we need to do the integration. So for x square, it is x cubed by 3. So that should be within the limit 0 to 1. If we put the value of 1 and 0 in this x cubed by 3 part, so in after several steps we will get the value of a1, this is equals to 500 by 12, so which is equals to 41.66. So again we are getting the same value of the trial function, which is similar to the point collocation. So the trial function equation, we are getting y equals to 41.66 into x minus x to the power 4. Next we need to find the value of a1 using the least squares method. Now in this least square method, we know that I equals to integration 0 to 1, that is the domain, r square dx, which can also be written as del I del a1, this is equals to integration 0 to 1 r del a1 dx. Now here in this numerical, the value of r, that is the residual, it is minus 12 a1 x square plus 500 x square. So that means del r del a1, this is equals to minus 12 x square. Now putting this value in equation number 6, we are getting the del I del a1, this is equals to integration 0 to 1 minus 12 a1 x square plus 500 x square multiplied by minus 12 x square dx. The requirement in this least square method, this is equals to del I del a1, this is equals to 0. And if we put the value of del I del a1, then after the multiplication, we will get that integration 0 to 1 144 a1 x to the power 4 minus 6000 x to the power 4 into dx, this is equals to 0. if we do the integration within the domain 0 to 1, then after several steps we'll get the value of a1 is 41.66. So the trial function value, again we are getting this same as 41.66 into x minus x to the power 4, which we got in case of subdomain and point collocation method also. And lastly, using the Galerkin's method, we need to find the a1. Now here, in case of the Galerkin method, we know the formula, which is integration 0 to 1, is within the domain wy rdx, this is equals to 0. But the trial function, this is actually here the weighting function. So that means integration 0 to 1 y rdx, this is equals to 0. So that means integration 0 to 1 a1 into x minus x to the power 4 multiplied by the residual, that is minus 12 by 1 x square plus 500 x square dx, this is equals to 0. Now after several steps we need to do the integration and we need to put the limit of the domain 0 to 1. Then after several steps we will get the value of a1 again as 41.66. So that means the trial function equation, it is y equals to 41.66 into x minus x to the power 4. So that means what we have got, that for all the 4 different weighted residual method, the value of a1 equals to 41.66 and the trial function, this is coming as 14.66 into x minus x to the power 4. So these are the things that we have discussed in this lecture. First we have discussed the boundary value problems, where we have seen how to take into assumption the auxiliary function, and based on that auxiliary function we need to put the value of the given boundary condition to find the ultimate equation. After that we have discussed the concept of the 4 different weighted residual methods, and based on those concept of the weighted residual methods we have discussed 2 different numericals, where we have seen that how to use the formula of the 4 different weighted residual methods, which are point collocation, subdomain collocation, least square method, and Galerkin's method. Okay, so this is the end for this lecture.